What's something people don't know about the universe? Imagine a world where the act of observation changes reality, where just watching an experiment can alter its outcome. Envision a universe where particles exist in a cloud of probability, always fluctuating and never in a single definite state until observed. Their destinies intertwined in ways that defy logic. These particles can influence each other instantaneously, regardless of the distance between them. Welcome to the fascinating world of quantum mechanics, a branch of physics that delves into the core of matter and energy at their most fundamental level. Quantum mechanics explores the very building blocks of reality, challenging our understanding of how the universe operates. It's a realm where the familiar rules of classical physics break down, replaced by a tapestry of bizarre and counterintuitive phenomena. In this quantum world, particles can be in multiple places at once, and their interactions can seem almost magical. Our journey into this strange and wonderful domain begins with a simple question: what is the universe made of? For centuries, physicists have sought to unravel this mystery, breaking down matter into smaller and smaller constituents. This quest led to the discovery of atoms, the building blocks of everything we see and touch. The atom, once thought indivisible, proved to be just the beginning of our journey into the subatomic world. Within its depths lay a subatomic world far stranger than anyone had imagined, a world teeming with particles and forces that defy our classical intuitions. The advent of quantum mechanics in the early 20th century shattered our classical intuitions about the nature of reality. It revealed a universe where particles behave like waves, where the dual nature of matter and energy challenges our conventional understanding, where certainty gives way to probability and the exact state of a particle can only be described in terms of likelihoods and probabilities, and where the act of measurement irrevocably alters the system being observed, collapsing the wave function into a single definite state. This is a world where particles can exist in multiple states at once, a phenomenon known as superposition, only collapsing into a definite state upon observation, a process that underscores the profound interconnectedness of the observer and the observed. It's a reality far removed from our everyday experience, yet it underpins the workings of our universe at the most fundamental level. Join us as we embark on an exhilarating exploration of quantum mechanics, a journey that will challenge our perceptions and illuminate the profound mysteries that lie at the heart of existence. Prepare to enter a realm where the impossible becomes possible, where the boundaries of what we know are constantly being pushed and redefined, where the very fabric of reality shimmers with uncertainty and wonder, inviting us to question, explore, and marvel at the universe in ways we never thought possible. This is going to blow your mind. At the core of quantum mechanics is the concept of quantization, a principle that fundamentally changes our understanding of the microscopic world. This revolutionary principle states that energy, like matter, exists in discrete packets called quanta. These packets are the smallest possible units of energy, indivisible and fundamental. Picture a staircase where you can only stand on specific steps, not between them. Each step represents a quantized level, a distinct and separate state. This is similar to the quantized nature of energy, where electrons in an atom can only occupy specific energy levels, much like steps on a staircase. They cannot exist in between these levels, only on them. This quantization of energy has significant implications for the behavior of atoms and subatomic particles. It dictates how they interact, bond, and form the building blocks of matter. It explains why atoms are stable and why they emit light at specific wavelengths, giving rise to the unique spectral lines that identify each element in the universe. These spectral lines are like the barcodes of the atomic world. It also underpins the workings of lasers, transistors, and countless other technologies that shape our modern world. Without quantization, modern electronics and photonics would not be possible. Another key concept of quantum mechanics is wave-particle duality, a notion that challenges our classical intuitions. This fascinating concept suggests that particles, like electrons and photons, can exhibit both wave-like and particle-like behavior. The famous double-slit experiment vividly demonstrates this duality. Imagine a beam of light, which we typically think of as a wave. This wave can spread out, interfere, and create patterns. Quantum mechanics tells us that this beam is also composed of countless particles called photons, each carrying a discrete amount of energy. These photons can be counted and measured individually. This duality is not limited to light, it extends to all matter. Even particles with mass, like electrons, exhibit wave-like properties. Electrons, the negatively charged particles that orbit the nucleus of an atom, can also behave like waves, diffracting and interfering just like ripples on a pond. This wave behavior is crucial for understanding chemical bonds and reactions. This wave-like nature of matter has profound implications for our understanding of the universe, blurring the line between the solid, tangible world we perceive and the ethereal realm of waves. It opens up a new perspective on the fundamental nature of reality. I don't think people understand just how mind-bending the double-slit experiment truly is. The strange nature of quantum mechanics is perhaps best illustrated by the double-slit experiment, a fundamental experiment in quantum physics that continues to challenge our understanding of reality. Imagine shining a beam of light at a barrier with two narrow slits cut into it. Behind the barrier, a screen captures the light that passes through. If light behaved solely as a wave, we would expect to see an interference pattern on the screen, with bright bands where the waves from the two slits reinforce each other and dark bands where they cancel out. This is indeed what happens, confirming the wave-like nature of light. However, the experiment takes a peculiar turn when we reduce the intensity of the light until we are firing individual photons, one at a time. Common sense suggests that each photon should pass through one slit or the other, creating two distinct bands on the screen. Astonishingly, this is not what happens. Instead, even though each photon is emitted individually, an interference pattern still emerges over time, as if each photon is somehow interfering with itself. This result implies that the photon, a single particle of light, is passing through both slits simultaneously, interfering with itself to create the observed pattern. This is only possible if the photon exists in a superposition of states, simultaneously passing through both slits until it is detected on the screen. The act of measurement, it seems, forces the photon to choose a definite path, collapsing the superposition and revealing a single spot on the screen. This is going to blow your mind. Entangled, the spooky connection of particles. One of the most perplexing and awe-inspiring phenomena in quantum mechanics is entanglement, a bizarre connection that can exist between two or more particles. Imagine two particles that are linked in such a way that knowing the state of one instantly reveals the state of the other, regardless of the distance separating them. This is the essence of entanglement, a phenomenon that Albert Einstein famously dubbed spooky action at a distance. To understand entanglement, we need to abandon our classical intuitions about particles possessing definite properties independent of observation. In the quantum realm, particles can exist in a superposition of states, and entanglement arises when two particles become correlated in such a way that their fates become intertwined. Imagine two entangled electrons, each with a property called spin, which can be either up or down. If we measure the spin of one electron and find it to be up, we instantly know that the spin of the other electron must be down, even if the two electrons are light years apart. This instantaneous correlation between entangled particles challenges our classical understanding of locality, where information cannot travel faster than the speed of light. Entanglement is not just a theoretical curiosity. It has profound implications for our understanding of the universe, and is at the heart of emerging technologies such as quantum computing and quantum cryptography. It underscores the deep interconnectedness of the quantum world, where particles can be linked in ways that defy our classical intuitions about space and time. Schrödinger's cat, a paradox of life and death. Schrödinger's cat is a famous thought experiment in quantum mechanics, proposed by Erwin Schrödinger in 1935. Imagine a cat sealed inside a box with a radioactive atom. The atom has a 50% chance of decaying within an hour. If the atom decays, it releases poison, killing the cat. If it doesn't, the cat lives. According to quantum mechanics, the atom exists in a superposition of states, both decayed and undecayed. Thus, the cat is in a superposition of states, both alive and dead, until we observe it. Observation collapses the superposition, forcing the cat into one state. This highlights the strangeness of quantum mechanics. Schrödinger's cat illustrates the counterintuitive nature of quantum mechanics and the boundary between quantum and classical physics. This was the end of the introduction of quantum mechanics. Stay tuned for our next video, where we will dive even deeper into the fascinating world of physics and quantum mechanics. You won't want to miss it.